Once again, ladies and gentlemen, you are all cordially welcome to today's lecture. This is the part we ended the last time. And we were able to look at something, and that something was the formulation of a linear programming preamble. It was a Final Ghana Limited that was producing 40 sachets of fan yogurt and 50 sachets. That was producing fan yogurt and fan choco. And the price per unit for fan yogurt and choco are 40 and 50 respectively. We were able to do this formulation, and we said we're going to address it using graphical method. So the purpose of this is to just demonstrate the graphical approach to this. I want to quickly ask you one thing. How many constraints are there in this formulation? You can tell me. Raise your hand and tell me. How many constraints are there in this formulation? How many constraints? Yes, Amana.
So we have 3 constraints.
3 constraints. Okay, that's very good. So we have 3 constraints. Sometimes the tendency is that a person will not include the non-negativity constraint, but you have to. You really have to include a non-negativity constraint. That is also part of it. Okay. Now, our job is to find the optimum, units of yogurt and choco to produce in order to maximize the profit, as you can see there. And to do that, we will start with the following. And please pay attention with me. Do what I'm doing and ask me the questions when it arises. All right. So at this stage, the first thing you want to notice is this. That to be able to, I want to write the formulation here. Okay. So the formulation is Z max, 40 x1 plus 50 x2 subject to the subject to is not coming the way it's supposed to come. Subject to what is happening today? Subject to x1 plus 2x2 less or equal to 40 hours, and then 4x1 plus 3x2 less or equal to 120, and then our non-negativity constraints. Okay, this was our formulation. So keep this in mind. Yeah, keep this in mind. Now at this stage, the first thing in order to do the graphical approach is to write the constraint. So this is our labor constraint. Okay, this is our labor constraint, and that is our milk constraint. So the first thing you want to do is to write your constraint, but you want to start with the non-negativity constraint. The non-negativity constraint is this very one here, right? That is this very one here. And the non-negativity constraint, what is interesting about the non-negativity constraint is that if you don't take care, you will not know how to draw it, but actually your Cartesian plane is your non-negativity constraint. Okay, drawing that Cartesian plane, which is usually something like this, that is a non-negativity constraint. I'm going to go to the next page and do that. So our non-negativity constraint is something like this, where we give this axis x1, and then we give this axis x2. And this point here, the point of intersection there is the 0. So it is referring to all the space, okay, the entire space from 0 upward, okay, the entire production possibility space from 0 upward. All this space bounded by the x and y axis, that is what is referring to the non-negativity constraint. So we've drawn the non-negativity constraint, finished. The next thing to do is to draw the other constraints. Okay. And what are those other constraints? Well, the other constraints are labor constraint and then null constraint. Now, in order to draw any of these constraints, there is something you want to note. You want to assume the maximum, limitations. And by assuming the maximum limitation, what it means is that you need to just use equal to sign to draw. And because there are two different units in the x1 and x2, it means that it becomes something like the equation of a line. Remember, your equation of a line is given by y equals to mx plus c. And the y and the x, okay, the y and the x are the things, the variables you don't know. And then the m and the c are what you know. So as an example, you can have something like 40 equal to 3x plus 10. Okay. Oh, sorry. Y equal to 3x plus 10. Y equals to 3x plus 10. And then your goal will be to plot this. So you're going to use the same principle to plot the x and the x1 and the x2. So the first one, we are going to write it as x1 plus 2x2 equal to 40 to show the limitation. Now, this is an equation of a line. So how do you plot an equation of a line? Well, if you want to plot an equation of a line, it's a very simple thing. So guys, be ready to answer me some fairly simple questions. One of them is this. If I want to know the value of x1, all I have to do is to assume that the value of x2 is 0. So let me ask you, if x2, okay, is 0, x1 is what? Who can tell me? You can raise the hand and tell me. Claire. Claire, unmute yourself and answer.
X1 will be 40 this case.
Exactly. So if x2 is 0, x1 will be 40. That's what it will be. X1 will be equal to 40. So now we go back to our plot to go and plot that so that we don't get lost. You have to do it. So x2 is 0. So you look at the vertical axis, x2 is 0. That will be on this 0 point. x1 will be 40. So you just identify anywhere here, okay, anywhere on the x1 axis and call it what? 40. That's what you do. Call it 40. Oh. Call it 40. So here you have a portion which I can decide to call it 40 here. And then I'll write my 40 there. Nicely. Then you now go back and go and calculate what if x1 is rather 0. So if x1 here is equal to 0, what will be x2? And you can tell me that very quickly. What will be x2?
X2 will be 20.
X2 will be 20. Okay, and for those of you who might not know, if this one is 0, then you have 2x2 equal to 40. 2x2 equal to 40. Divide both sides by 2. 2 cancels 2. 2 goes into 40, 20. See, so that's how he got the 20 there. See, sometimes for beginners, if some of these things, someone is mentioning them and you don't know where they are coming from, it can be confusing. So let me just tell you, x1 is 0, so you're going to have 0 plus 2x2 equal to 40. Okay, so you have 2x2 equal to 40. Divide both sides by 2, divide both sides by 2. Okay, this 2 cancels 2, and then 40 by that is 20. So now we know that if x1 is 0, x2 is 20. So you go back. Okay, x1, this axis, x1, which is x-axis, is 0. Then x2 is 20. So you can identify anywhere here and then call it what? 20. And then you can nicely write your 20 here. Now that you've been able to get 2 points, you can easily join them because equation of a line, you only need 2 points. So you just write your 2 points there. Beautiful. And then you can now write this equation, okay, and say that this line is actually x1 plus 2x2 equal to 40 for the line. Now you are done. You've been able to write the first constraint. Are you guys with me so far? If you are with me so far, just type yes, 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 and I'll be smiling. Now, the next thing to do is you move ahead and then you can now go to do the second equation. So let's go to the second equation. The second equation says 4x1 plus 3x2 equal to 120. You are using the limit. So let's write that. Okay, I'm going to write that here. 4x1 plus 3x2 equal to 120. So once again, if x1 is 0, x2 will be what? So if x1 is 0, x2 will be what? Who can raise a hand and tell me? If x1 is 0, what will be x2? Let's go to Ebenezer. Ebenezer, what will be x?
S2 will be 40.
X2 will be what? You sound very far away.
S2 will be 40.
Okay, S2 will be 40. So you now write a 40 there. Okay, you write a 40 there, and let me just delete this. You write your 40 beautifully and nicely captured there. So you see, what you are doing, if you understand one principle, you can do the rest. So x1 is 0, x2 is 40. So you come to the axis, x1 is 0, all right, on the axis is 0, x2 is 40. 40, is it going to be above the 20 or below the 20? If you have a mathematical eye, you will know that the 40 will be above the 20, not below the 20, not at the 20, but above it. So you just write 20 there. Just identify a point and call it what? 40. And now we go to the second one. Now, in the second situation, what if x2 is rather 0? If x2 is 0, x1 will be what? You can tell us. S1 will be what? If x2 is 0, what will be s1? Oh, for Suhine.
That would be. Is which of the equations?
We are using the equation you see here. There's only one equation.
The 4x1.
Yes, that one. You didn't prepare. If you didn't prepare, no problem. Let somebody else.
No, I didn't see the equation.
Okay, but we have been dealing with that equation all this while. So it means that you are probably
30.
not. So I understand. Just that next time, just follow us, okay? You weren't following. You didn't know what I was doing there. So next time, just follow us so that we can have a smooth sail. Okay. So you're going to get 30. You're going to get 30 there. And so you come to your axis. Once you come to your axis, you can now plot that on the axis. Okay, so x2 is 0. So on this vertical axis, you get 0. And then x1 is 30. 30, is it going to be to the right or to the left of this number 40? Will it be to the right or to the left? Kajitan?
It's going to be to the left.
To the left, exactly. And thanks, Amana, for raising the hand as well. So it's going to be to the left. So you identify somewhere here, all right, and just write your what, 30 there. And now you're going to join that 30 with this 40 there. And boom, you've been able to capture the constraint. At this stage, you've been able to get all of these necessary constraints. But there's something you want to note here. Okay, if I were to identify an area, so there are two areas here. The first one is the labor constraint area. The labor constraint area looks at the 20 to the 40 line, the 20 to the 40, 2040 line, 2040 line, and all the space towards the origin. The 2040 line and all the space towards the origin. That is a labor constraint area. Now, the milk constraint area will be the 40-30 line. The 40-30 line and all the spaces that are below that line towards the origin. Okay, of course, bounded vertically by the y-axis and horizontally by the x-axis. So you can see that that will be, so we have two constraint areas. Now I'm going to identify some points for these constraint areas. Okay. Oh, someone says he's not getting the 20, 40, 30, 40. Okay, so let me just give you the labor constraint area. It starts from, the labor constraint line is x1, 2x1. That is labor. So this line here is labor. Now this line that we did was the 4x1 plus 3x2 equal to 120. So that was this line, okay, is a 40, 30, the 40 at the top, the 30 at the down. That line, the spaces on the left, let me just shade some of those spaces on the left, okay. The spaces here, let me shade some of the spaces for that, just for you to see. Okay, so these spaces, that is what we mean by the 40, 30, and that is for milk. So this one was for milk, this was for milk, and this was for labor. So if you look at the milk constraint, this 40-30 line and the area to the left of it, which I have just shaded, okay, this area, that is what is representing the milk constraint area. Okay, but then if I should look at the labor constraint area, it will be the 20-40 line. 20 at the top here, all right, the 40 at the bottom right, and the spaces. So that will include this empty space as well. That is the labor constraint area. Now, the labor constraint area as well as the milk constraint area, there is an area that is common to them. So first, let me identify some of the areas. You have A here, you have B there, you have C there. Okay. See the areas I've just indicated. A, B, and C. Okay. A, B, and C. Now guys, if you look at A, B, and C, which area is common to both the labor constraint area and the milk constraint area? Who can tell us? Which area is common? Ebenezer?
Area B.
Is a B. Is a B. Exactly. So now that we know what area is a common, that area is said to be the feasible solution area, FSB. Okay, so area, and we are talking about the area bounded by this line here, that one there. Okay, now that area, which is now the ones I've shaded here, that area is the feasible solution area. Feasible solution area. Now, why is that so? Well, now if you look at the feasible solution area, that feasible solution area is the area said to be common for both constraints. Okay, common for both constraints. It is the area on the graph which is bounded by the constraint equation at any point on this polygon, or any point on its interior is said to be feasible region. Okay. It's said to be a feasible region. So when you look at the corners of this area, which is what we are going to concentrate on, the first corner is this. If you look at them very carefully, there are corners. Okay. And let me just pick a certain yellow line too. So this is the first corner. The first corner is where I'm shading. That's the first corner. It's a corner point. It's an extreme corner point. This is another corner where the two lines are meeting here. And this is another corner where the points are meeting here. Of course, the 0, 0 point here is also another corner. So the whole space, if you have to join these spaces, it becomes like a polygon. Okay, a lower version of a polyhedral. Now, listen please carefully. That corners, those corners that you are seeing here are very important. I'm going to label them, the corners. I'm going to call this one corner point B, corner point A. Okay, let me do capitals. Corner point A, corner point B, corner point C, and then corner point 0, as you can see there. These corner points are very important if you are beginning to find the point. Now remember, what is our goal? Our goal is to find x1 and x2 points. So anywhere on this space, this feasible solution area, inside it or on the vertices of it, and you are going to realize that we are going to focus on the vertices. Okay, on the vertices of this polygon, okay, the vertices, one of them is going to be the feasible solution area. One of them should be the feasible. Obviously, it's not going to be 0, 0. So that one is out. Because remember, our goal is to find the x1 and the x2. And the x1 and the x2 is either at point A. And when you look at a point A, there are some things that are there. Okay, the x1 will be 0, the x2 will be 20. Look at point A. Look at point C. The x1 will be 30 and the x2 will be 0. And look at point B. As for point B, we don't know the point. We don't know the coordinate. Okay, but we're going to find out. And we'll use a certain approach to be able to find out. Now, one way to identify graphically this feasible solution area, one way to identify it graphically is by drawing an isoprophet line. Drawing an isoprophet line. I'm going to show you what I mean by an isoprophet line. Guys, do you remember the Z formula? The Z formula. Let me just show you here. Okay, the Z formula, the objective function formula, is given by Z. Oh, let me just clean this before. It's given by Z equal to 40x1 plus 50x2. All right, this is the Z formula. Now, what we are going to do is that we are going to create an isoprophet line for this Z. Now, how do you create an isoprophet line? How do you do that? Ebenezer, please just watch your microphone very carefully. How do you create an isoprophet line? Well, you can make an assumption. And let me just go to the next page to do that. Okay, Z is equal to 40x1 plus 50x2. Now, you can assume a number. Let's assume a number. Okay, and you can assume any number. And the best way to get an assumed number, first assume the number, is by multiplying the 40 by the 50 and dividing it by 2. Okay, so you take your calculator and then you multiply 40 by 50. And you just give it, this is just arbitrary. You have to do any other means to get it. Okay, 40 by 50 is 2,000. And then you divide it by 2. Okay, so 40 times 50 is equal to 2,000. And then when you divide the 2,000 by 2, that gives you 1,000. So I'm going to assume that this Z value is 1,000. It's just an assumption, just to create an equation of a line from it. So Z value is 1,000. So you write 1,000 equals to 40x1 plus 50x2. All right. And then you now ask yourself, if x1 is 0, what is x2? Okay. So here, if x1 is 0, okay, x2 will be 1,000 divided by 50. And 1,000 divided by 50, okay, you can now take your calculator and then find the answer to be 20. Okay, so if x1 is 0, x2 is 20. And once again, if x2 is also 0, then x1 is what? 1,000 divided by 40. And that will give you 25. So you get 25. So what is happening is that you have a point which is x1 to be 20, sorry, x2 to be 20, and then x1 to, sorry, x2 to be 20, x1 to be 25. So you go to your graph, and then you go and identify those 2 points. x1 is 25. So x1 is 25 will be somewhere here. All right? And then x2 will be 20. That will be somewhere there. All right? That is somewhere there. Okay. So you have 25. For 25, I need to just come down a bit. Remember, these things are not drawn to scale. Okay. So 25 and 20, if I were to join this line, it would be something like that. So that line I've just drawn is a line for 1,000 profit. This line, which I've just drawn, where you have 20 there, and then you have 25 there, is called an ISO profit line. The ISO profit line. Now remember, the number I selected was 1,000. If I should select a number like 800, okay, which is equal to 40x1 plus 50x2, you can choose any number like I said. Okay, if I should select a number like that, the line will come down. The line will come down somewhere down here. But it will be parallel. Okay. And if I should select a number that is bigger, like 2,000, right? 2,000, okay, which is equal to 40x1 plus 50x2. If I should select a number like that, the line will be, you know, above. It will go above somewhere like that. Okay, but it will still be what? Parallel. So here is the case. The point is that once you get the 800 line, which is the first one at the bottom here, then the one we did, which is 1,000, the idea is to keep shifting that line parallel upward. You keep shifting it gradually. You keep shifting it gradually. So you keep shifting this line, you keep shifting it upward until the last corner it leaves. Now remember, I've not drawn this thing to scale, but if you should have a graph line and you are actually shifting it gradually upward, gradually parallel upward, gradually parallel upward, okay, and it will, the last corner it will leave. Remember, there are 3 vertices. Okay, the last corner before this line, if you look at the way it's moving, the last corner before it leaves the feasible solution area, that will be the point B. That will be the point B. That will be the point B. And that is the section which will be. And so once you identify that that is a point B, now what you will do is that you have to trace that point B downwards. Okay. So you have to take that point B and then trace it down. Okay. And that point B, and then trace it leftward. And that will be where it's going to meet. Okay. So look at this. That will be where it's going to be, this section here. That is where it's going to meet. Let me just remove some of these lines. Okay. That will be where it is going to be meeting there. So this section here, and then there, that will be where the line will be meeting. Amanda, your hand is up.
Sir, please, I have a question.
Please go ahead.
So with the B, do we put any figure there? Because if the expression is given to us, would the figure for B be given or
No. If you are doing a graph, when you trace it down, okay, and let me just go and trace it down again. When you pick this thing and you start tracing it down, you will read the actual value on the axis. And when you take this and you trace it leftward, you will read the actual values there. So graphical approach is nice, but if you don't have a proper graph, a graph with numbers well indicated, you cannot really show the graphical approach. So the only way we show the graphical approach is that we have to add the mathematical approach to the graphical approach, which we are going to do now to know the exact values at B, at point B. Do you get it?
Yes, sir.
Perfect. So let's do that now. Yeah, ladies and gentlemen, just work with me now to do that. So I'm just going to clean this so that I can use this space for that for you to see, which you are going to really, really appreciate and like. So we are going to get the line. Remember, there are two lines that are meeting there. If you check carefully, at point B, you have this first line, which is a null constraint line. And then you also have the labor constraint line. They are joining. Where two lines are joining, you can find the point at that line using a simultaneous equation. First of all, as it stands, it looks like these two equations are simultaneous equations. Let me rewrite them for you to see. Okay. The first constraint was x1 plus 2x2 equal to, now I'm using equal to just to indicate the limits. And then you had 4x1 plus 3x2 equal to 120. Doesn't it look like simultaneous equation? Of course it does. Of course it does. Now, simultaneous equation, you can solve it easily. How do you solve it? Well, you can use the elimination method or you can use the substitution method. Okay. I want to use the substitution method. Okay. If I call this one equation 1 and this equation 2, I can move the x2 to this side. Okay. And so I can have an equation 3 to be x1. Okay. x1 equal to 40 plus 2x2. Okay, so that gives me something like an equation 3. And in substitution method, now that you have equation 3, which you generated from equation 1, you can just drop the equation 3 into 2, wherever you see x1. Yes, Stephen, your hand is up.
Please, the equation 3, is it 40?
Yes, I just derived it from equation 1. So it's 40 plus, oh, sorry, it's 40 minus. Is that what you meant?
Thank you.
All right.
Thank you.
Yeah, thanks for that. So it's 40 minus 2x2. 40 minus. So you're going to put this 40 minus 2x2 into the above equation 2. So, yes, Morrison. It's hand up again. All right. So you're going to rewrite it as 40. Oh. You're going to rewrite it as 40, and instead of x1, you will substitute the information for x1 into bracket 40 into bracket 40 minus 2x2 close bracket plus 3x2 equal to 120. Okay, equal to 120. And at this stage of finishing your 120, you can easily solve this equation. Okay, you can solve it. You can multiply 40 by 40. Okay, and that will be 1006. So you get 1006 minus 80 x2 plus 3 x2 equal to 120. Now, you can group items. Oh, I made a mistake. This is supposed to be 4, okay, not 40. So that will be 160. Maybe somebody wanted to remind me of that. So this one will be 4, 160, and that will be 80. So you get 4 times 2, 40 times 4, which is 160, and then you can have it like this. Okay. All right. So at this stage, the next thing you want to do is you just have to group items and then solve for the value of x2. Okay. And you can move this one there, and then you can move this one here. So if you move these ones to the right hand side, you get 80 and then plus 80 and then minus 77. I just want to be sure that I've been able to get it correct. So this is minus 8 here. So let me just quickly correct that. So it's not 80. Oh, I've cleaned this again. So it's 40 minus 2x2 2. The system is just not allowing me to be able to write these things well. 2x2. All right. And then the number outside is supposed to be 0. It's supposed to be 4. Okay. And then what is inside is supposed to be 0. 40. So you get 8x2. You can just go and look at it. Okay. You can just get it. And so you get 160. And then you bring the one on the left, minus 120, equal to 8x2 minus 3x2. So what I've just done is to group like terms. Okay. And when you group like terms, 160 minus 120, that's obvious number. 160 minus 120. Okay. And that will give you 40. Okay. And then you now have 8 minus 3. That will give you 5. So you get 40. I don't know why this thing keeps coming. So you get 40 equal to 5x2. You divide both sides by 5 and x2 is equal to 8. So now you have the value of x2 to be 8. Normal simultaneous equation. Now substitute that one into your equation 3. Substitute that into your equation 3. And your equation 3 is x1 equal to 40 minus 2x2. So that gives you 40 minus 2 into bracket 8. And when you do that, that'll give you 24. So your x1 is 24. Let me just use some different color. Your x1 here is 24. Your x2 is 8. So the values that you wanted from this junction, okay, this x1, the actual values you wanted was 24. So the value was 24. That's what you want here. And then here is the value is 8. So now you know the vertices for B, the coordinates for that. Now what are the coordinates for A? Well, at this stage you can see the coordinates for A are x1 to be 0, x2 to be 20. The coordinates for B are, we just found them, x1 to be 24, x2 to be 8. Always write x1 first. And the coordinate for C, you don't need to, if you really want to mention it, because there's some bit of noise that keeps coming. And I got worried, unless the person has raised their hand to work with me. So you get C equals to 30 and then 0. So these are the coordinates, okay? And we now know graphically that the last point that the isoprophet will leave the feasible solution area is a point B. Okay? But you want to prove that fully. You want to prove whether point B is the true, coordinates. Because you need to also find the z value. You need to find the z value. Okay? So how do you do that? Okay. This is how you do it. Remember, your equation is z equal to 40x1 plus 50x2, okay, subject to, okay, x1 plus 2x2 less or equal to 40, 4x1 plus 3x2 less or equal to 120, your x1, your x2, that's a non-negativity constraint, positive. Okay. So this was the equation that you dealt with. You now know the coordinate. So in order to get the actual values for z, you have to put in each of the coordinates on the vertices into the z to find which one will give you the greatest z value. Why greatest? Because you are making profit, so you want the biggest profit. So the one that will give you the biggest profit is the ultimate. So let's substitute. So z at the point of A, we're going to calculate them. Then we'll calculate z at the point of B. Then z at the point of C. Which one gives us the highest? Now for the first one, A, 40x1. 40x1. Now if you look at the x1 at the coordinates of 40, you will see that x1 was 0, x2 was 20. So you go and substitute it there. x1 was 0. So x1 is 0, and then 50, x2 is 20. When you do that, 40 by 0 will give you 0. 50 by that will give you 1,000. So the profit you get there is 1,000. Now let's do the same thing, okay, for the second situation. For B, the value of x1 was 24. The value of x2 was 8. So you have 24 and then 8. The question is, what is it going to be? 40 times 24. 24, 16, 4, 50 by 8. So you add the 2, that will give you 1,360. So you get 1,360 cedis. That is the profit you make at that point B. Now let's look at point C. If you look at point C, you have 30 for the x and 0 for the x2. 30, so you have 40 multiplying 30, and then 50 multiplying 0. What do you get? Well, you just get this first one, which is 1,002, because 40 by 30 will give you, 1,002. So you get 1,002. So in all of these z values, the one that gave you the highest profit is again point B, which goes to confirm that point B is truly the optimal solution. The optimal solution. Now, point B, the coordinates there, the 24 and the 8, are known as the feasible solution point. The feasible solution point. Solution. So what this means is that if Fan Ghana Limited produces 24 Fan Yogo and 8 Fan Choco, it's going to make a profit of 1,360 at the point B. And point B is the ultimate situation that we have there. So this is a very, very powerful analysis. Let's take it to the slides. And you see that the slides has identified all of this. If you go and check the slides, everything we did, this is where we're shifting the lines up and down. You can see all of them there. Okay? You can see all of the shifting, the coordinates, the point, the feasible solution. And then at each corner point, the values we had, 1,000, 1,360, 1,002, all of them, we calculated that. And then the simultaneous equation that gave us the actual answer is there. And the final z value is what we have there. It's a very beautiful way. However, there are certain things that could happen. Sometimes if you want to be sure that the point you have is truly optimal, the next thing you want to do is to substitute the information into the constraint, okay, to be able to identify that there are no slacks. Okay. So let me just remind you, these are our point. In order to prove that this is even optimal, the point B is truly optimal, not just a necessary condition, but a sufficient condition. Let's watch something. Take the coordinates of A and substitute it into the constraint, the labor constraint and the Null constraint. What are the coordinates? They are 0 and 20. Now look at the labor constraint. Okay, look at the labor constraint here. This is the labor constraint. So I'm going to substitute these values into the labor constraint as well as the milk constraint. What happens? The labor constraint as well as the milk constraint. Well, x1, if you look at it, it says x1. So x1, I pick the point A, that will be 0, plus 2x2, and x2 was what? 20. So at that point, you have 20. Let's see the answer to that. The answer you get when you multiply that is what? Is equal to 40. What that means is that that coordinate will make the labor constraint binding. Binding. Now, what do we mean by binding? A binding constraint is where the left-hand side of the equation equals the right-hand side of the equation. What it means is that all the available resources have been fully utilized. all the usage equal to all the available. And when you take the coordinates of A, it does that. But the question is, does it do the same thing to the null constraint? Let's go to the null constraint. Okay, that is 4x1. x1 is what? 0. So you have 4, 0, okay, plus 3x2. Okay, x2 is what? x2 is 20. 20. And according to the rule, oops, let me just clear this. Okay. According to the rule, this should be equal to 120. Now watch it carefully. You can see that this will be 0, but this will be 60. Okay, and 60 is not equal to 0. Okay, but 60 is less than 120. 60 is less than 120. So what does that mean? What this means is that this second constraint is not binding. So this is not binding constraint. Not binding. So you can see that at a point A, okay, it's not a matter of the fact that it's giving us only a lower profit, but it's also giving us a non-binding constraint. Okay, a non-binding constraint, and you don't want that. In fact, when you go and do the same thing to C, and you substitute the coordinates of C into both constraint labor and constraint milk, you will see that one of them will be binding, the other will not be binding. Now, sometimes you might even find it strange that all of them might not be binding. But let's do the same thing to point B. Point B. Okay. Now, point B, you have the coordinates to be what? 24. Okay. You have 24, and then you have the other one to be 8. Let's put the 24 into the labor constraint. So labor constraint will be 24 plus 2x2, and that's 8. Okay. 24 plus 2x2. Okay. 2 times 8 is 16. 16 plus 24 is actually 40. So that's binding. Okay. Let's do the same thing to the null constraint. It is 4x1, and x1 is 24. So I'll put that in the bracket, plus 2x plus 3x2, and the x2 is 8. Okay. Let's see whether that will be equal to 120. 4 times 24 is about 96. 3 times 8 is 24. When you add that, that is exactly 120. So equation, the labor constraint and then the null constraint, they are all binding if you drop the values of B into each one of them. Okay, so you can see that B is the true optimum solution graphically, and is a true optimum solution because it gave us the highest profit. Okay, and then it also gave us the most binding constraint. Now I must say that it's not all the time that's the one that will give will give you all of the constraints to be binding, but in this context it has done that. So B is a true optimal value. Now let's go back to when we dropped A. Do you realize that when you dropped A and you calculated the milk constraint, we had a value of 60, which is not up to what? Up to the 120. But you see, the 60 is still within the feasible solution area. Okay, so when you go to this situation, the 60 will be inside the area, but it will not be on the corners, or it will not be on the lines. Okay, but the 120 is on the line. So it means that this if you should get the value of coordinates of A, the 60 will indicate that there is a slack. There's a slack. There's a slack of 60. There are unused resources. I will come back to the details of this better, okay, when we bring the Excel into the picture. There are unused resources, leftover gallons of milk of 60. You can see that here. But you can see that looking at the coordinates of B, there are no leftovers. There are no leftovers. All of them have been fully utilized. The left-hand side is fully equal to the right-hand side. And that's what you want in any company. You want a company where resources are fully utilized. If you say 8 hours a day, you don't read the newspapers for 2 hours. Okay? You utilize, you ensure that all the hours are fully utilized. And that is the beauty of the way that you have to analyze this linear programming problem. at the optimum solution, okay, those are the few things, okay, altering the objective function coefficient will lead to a new solution. So that's one thing you should note. Okay. So the solution is very sensitive to the values of the coefficient. And we'll look at this better when we come to the sensitivity analysis. If you change the constraint, the solution space, things will happen. Okay. I've spoken about slacks, but I'll just talk about them later on again. When we say slacks, we are referring to unused resources. So if you look at the B point, you realize that there was no resource that was left over. All the resources were fully utilized. And so you want to know that when it comes to situations related. Okay. So a slack contributes nothing to the objective function. So it will yield no profit. And it's given a value of 0 in the objective function. And we'll come and learn something we call the standard form. Okay. We'll come and learn that. I think we have to even learn the standard form now. Okay. So let me quickly show you something about the standard form now. So there's something you need to know about the standard form of the linear programming problem. The standard form is a very simple approach, but it's a very, very interesting approach as well. You see, the standard form requires that, so sometimes you have the non-standard form. So the linear programming that I gave to you, let me just show you again. Z equals Z max equal to 40 x1 plus 50 x2 subject to x1 plus 2x2 less than or equal to 40 4x1 plus 3x2 less than or equal to 120 120. Oh, where am I? I'm lost again. 120, and then x1 comma x2 greater or equal to 0. This is known as non-standard form. It's not the standard form. A non-standard form. So we have to convert it. Sometimes you are supposed to converting it to the standard form is a very simple approach. What it simply means that we don't want these. We don't want the less than or equal to. We want everything to be equal to. You want everything to be equal to. And how do you do that? First rule, you write them in the form of slacks. You use the slacks to write them. And what are the slacks? I told you earlier, the slacks are the amount of unused resources. So what is amount of unused labor? And you have to represent the slacks with something. And the number of slacks are equal to the number of resource constraints. The number of resource constraints. So you will say that let S1 be the number of slacks for labor. Okay. Let S1 be the amount of unused labor. Let me just put it that way. Amount of unused labor. That is S1. Okay. S2 should be the amount of unused milk. Now, the reason why we chose S1 and S2 because there are only 2 constraints. If there were 3 constraints, we will have S3. And when I say constraint, I'm talking about resource constraint. Resource. If there was a sugar constraint, we will have S3. If there was water constraint, we will have S4. So the number of constraints defines the number of S's, the slacks. The S is referring to the slacks, which is the leftover or the unused resource. Now, in the objective function, we need to introduce the slacks and attach zeros to them. That is it. When you are writing the standard form, that is how you. So in the objective function, okay, attach zeros to the slacks. Attach zeros to the slacks. So you write the slacks as S1 and S2, but you attach zeros to them. You will write them, add them, but then when you're attaching zeros to them, what is simple you are trying to say is that they do not contribute anything to the objective function. And it's true. Let me give you a practical reason why this intuition is good. Slacks are resources you didn't use. So let's take some hours. You were supposed to spend 7 hours yesterday. You did not spend that 7 hours. So how is that 7 hours you did not spend, how is it going to contribute to the profit of yesterday? There's no way you contribute. Once you don't use it, these resources are gone. Resources are limited. If you don't use it, if you don't use the hours, you don't say that I'm going to work overtime to replace those things. Okay? That is not how the systems are designed. Most systems are designed in such a way that once you don't use them, they are gone. And so if they are gone, then they do not contribute anything to profit, the Z value. And that is a principle that we have. But then the slacks contribute, the slacks will show in the constraint. So when we go to the label constraint, the slacks will show there. When we go to the capital constraint, the slacks will show there. And if they are showing there, then the inequality sign might change to equality sign. Okay. So I'm going to rewrite the whole equation in a standard form for you, so that you will know how to write indicators. So let's rewrite the whole thing in a standard form. So in a standard form, you write Z. Oops. I don't know why this thing keeps happening like that. In the standard form, you have Z max equal to 40x1 plus 50x2 plus 0s1 for the first slacks plus 0 S2 for the second slack. If there was a third slack, we would have written it like that. Okay, that is how you formulate the objective function. Okay. That is how we formulate the objective function. Then we go to subject to. So you now have your subject to, then x1 plus 2x2, and then this time you have a slack. Okay, so you need to add the slack to it. So plus S1, then you make it equal to, not inequality again, equal to 40. I'm going to explain to you, because if the slack happens to be 0, then this section here, okay, then the left part here, x1 plus 2x2 is actually 40. But if x1 plus 2x2 is not 40, then it means whatever is left unused, the leftover becomes a slacks. Okay, the leftover becomes a slacks. So the second one will be 4x1 plus 3x2 plus s2 equal to 120. Now, so at this stage, if you want to know the value of the slacks, okay, if you make s1 the subject, okay, it will tell you that the slacks is actually the right-hand side minus the left-hand side. I'll come back to that. But let's write the non-negativity constraint. That is x1, x2, and this time the slacks must also be non-negative. So you have to attach s1 and then s2 to it and make it all non-negative. That one will not change. That one will have to still maintain the inequality sign of greater than or equal to. So what is s1? Well, if you look at it carefully, s1, if I want s1, it's just a matter of moving everything to the right-hand side. And that is a matter of this right-hand side already here minus the left-hand side already coming. So slacks is actually defined as the right-hand side value minus the left-hand side value. Okay, and this slack 2 will also be the same as the available resources minus the used resources. And that eventually gives you the unused resources. Okay. So the way I've written it, you can see that in terms of the real situation, I have introduced slacks throughout, and that changes the inequality sign to the equality sign. Non-negativity constraint doesn't change slacks because it's just what it is. Okay. This is very important because in some situation, you will need everything to be equal so that you just do it an easy way. And learning how to write it in the standard form is very important. So that is a standard form. That is a standard form. And remember, this is a maximization. So the slacks are added to the constraints on the left-hand side. But if it was a minimization, okay, if it is a minimization, what we will do, and I will teach you a minimization, don't worry. If it is a minimization, you will realize that the slacks will have to be subtracted from that of the constraint. Okay. And of course, the principle, some of the terminologies in the minimization are different because we don't talk about slacks there. We talk about surpluses. We'll come to that. We'll come to the minimization. So, any question at this stage? So, like I indicated, I'll be taking you through the minimization. Okay, next time. Okay, minimizing, not maximizing, but minimizing, so that you be able to understand it too. Then we'll look at irregular types of linear programming, okay, such as the multiple optimal solution, infeasibility, unboundedness, and redundancy. We'll look at all of that, okay, so that you come to appreciate this whole thing. And then after that, we will also consider a case problem. And then I'll give you an assignment, and that will end the first part of this. Then when we meet the next time after that, to be a manual computation of the simplest method, using the simplest method on itself. So, ladies and gentlemen, what a way to, get to the nitty-gritties. Those are some of the references you can look at to be able to appreciate what we have done so far. These are some of the papers that have been written when it comes to these linear programming and OR and all of that. But we are going to meet next time. Always remember to drink deep, or taste not the Pierian spring. There shallow drought will intoxicate the brain, and drinking wisely sobers us again. Welcome to the Valley of the Shadows of Operations Research or Management Science.